The next section we need to understand is about Erwin Schrodinger and his equation. This, at the bottom, is his time-dependent equation, which basically tells the position and time and the probability of finding it at different places in the atom. And you need to be studying university level physics to be able to understand or use it. So fortunately, we don't need to do the maths with this, but we just need to have an idea behind what's going on. So we'll look at what we basically need to know. I'll do it in a quick summary, then we'll go into the details and we'll summarize it again. So, Schrodinger. He used de Broglie's idea of the electron, which behaved like a wave, and decided that the electron could be described by a probability wave function. And what this means, that this function, this wave function, gave the probability of finding an electron in a particular place at a particular time. So that's the way he used this idea of waves as a probability function. So this equation we don't need to know. I might refer to this term here, the psi. Psi squared, by the way, gives the probability. And for this, he got the Nobel Prize for Physics in 1933. He actually did the physics 10 years earlier, but he was awarded the Nobel Prize for Physics in 1933. So let's look at the details here. This is his model. The IB say this assumes that electrons in the atom may be described as wave functions. The electron has an undefined position, but the square of the amplitude of the wave function, this psi squared, gives a probability of finding the electron at a particular point. These are things that we basically need to remember. As I say, you don't need to use the maths, but you need to remember the ideas behind it. And the key words I've basically underlined or emphasized in red. So the Schrodinger model. So he assumes a wave function which is associated with the electron in the atom, and the idea was from de Broglie. This wave function is a function of position and time, and it's basically a probability function. It gives a probability that an electron will be found in a particular position at a particular time. The electron is a kind of fuzzy entity. It has an undefined position, but the square of the amplitude of the wave function gives a probability of finding it at that point. That's basically what we've said already. This wave function has got quantized energy, a bit like the wave in a box. Only certain waves, therefore certain momenta, therefore certain energies were allowed to fit inside this box. The electron can only be found in certain energy levels. These levels have to fit the boundary conditions. Remember, with the standing wave, in a classical standing wave with a guitar string, for example, the boundary condition is that it's a node at either end. But this is boundary conditions in 3 dimensions, giving rise to radial and angular modes. But we don't need to deal with those details. The key point is that it has to fit the boundary conditions within the atom. This is interesting. When the electron is actually observed to find out where it is, we say that the wave function is to collapse. This probability function is no longer indeterminate, it's determined. Then as soon as you have made the observation, then the electron goes back to being a particle, not a probability function. So, a summary. 6 points. The wave function is a function of position and time. The square of the amplitude of the wave function gives a probability of finding it at a particular point at a particular time. The wave function is quantized, a bit like the wave in the box model. Sometimes you can have basically a superposition of 2 or more states. In other words, it can be one position or another position, or a superposition of both. And this is why we say it's an indeterminate state. A bit like flipping a coin. If you flip a coin, it could be a heads or tails. You put your hand down on the coin. Is it a head or tail? Well, in quantum physics, we say that it's this indeterminate state. It's both at the same time, the superposition of being both heads and tails, until we observe it. When we observe it, then we're able to do it becomes a head or a tail. But until it's observed, it's this indeterminate state. This wave function needs to fit the boundary conditions. When the observation is made, the wave function is said to collapse, and then we'll see it's in one location. Here is an example of what the wave function looks like. This is a graph of psi against distance. If you imagine the square of this graph, we've got a high probability of finding the electron in this position. There is some chance of finding it here, but it's not so likely. There's some chance of finding it here, but that's not likely either. At this point it's 0. There's no chance of finding the electron 0 nanometers from the nucleus. In other words, it will not be found in the nucleus. So here, this is the psi probability wave function for hydrogen. The electron is represented by this probability wave, and psi squared gives that probability. So here we have a view of the nucleus, and the dots, this cloudy dot area, is basically where we think the electron will be. Now, according to this, it's more likely to be here in this area than it is close to the nucleus or around the outside. So it's basically the probability of finding it at a particular position. As you get to higher and higher energy levels, it becomes more and more complicated. So there's no chance of it being found here, but there's a high chance of it being found here. It depends on which order of the wave you're referring to. Here's an example from a past paper question. This is the psi squared. According to Schrodinger, it's more likely to be found at A than it is here or here. It is possible to find it at this distance, but it's less likely than A. So it may be deduced from the distance that the distance of the electron from the nucleus is most likely to be near A, is always A, is always less than A, or is always greater than A. So let's go do these backwards. It's always greater than A. Is that correct? No, because it can be less than A. Is it always less than A? No, because it can be greater than A. Is it always A? Well, no, it can be less and it can be greater. So this has the highest probability, so it's more likely to be found at A than any other position. This is a level of understanding we need to have. Now, of course, you know Schrodinger is known for his mistreatment of cats. And this is where they have some kind of a society for the prevention of cruelty to animals called on Schrodinger to have a word about what is his cat, because he has this cat in this box, and he kills the cat basically. But of course, he doesn't kill cats. He doesn't. He's not a nasty person. His ideas that he has are being used to describe this condition, this Schrodinger's cat, which is very misunderstood, but we need to look at this now. So this is Schrodinger's cat. The cat has been placed in a box. Inside this, there's a poison, there's a hammer, and there's a radioactive material. Now, you know that radioactivity is a random process. And what happens is that once the Geiger counter picks up that there's a certain amount of radioactivity, when there's a certain decay, and you never know what that is because it's a completely random process. So it's all to do with probability. When there's a decay and you never know what it is, this will pick up the decay. The scissors will cut the string, the hammer will smash the poison, and the cat will. Okay, so what are the alternatives? What could happen? Well, we have two alternatives. Either the cat is still alive, in other words, the material has not decayed and it hasn't smashed the vessel with the poison in, or it has decayed and the poison has been opened and the cat has died. So we have this indeterminate state of being both alive and dead at the same time. So which one is it? Well, according to Schrodinger, it's that the cat is both alive and dead. This probability function can only be collapsed when we open the box and actually see if the cat is alive or dead. So here we have it. So basically this is it. A cat is put in a box with a radioactive source. In time, the radioactive source will cause the death of the cat by releasing a poison, effectively. Now we know radioactivity is a random process and you never know exactly when the cat is going to die. As soon as you close the box, is the cat alive or dead? You can say you would say it's either alive or dead. But no, in terms of quantum physics, it's in this state of being both alive and dead. This indeterminate state, according to the laws of probability. So it's in a state where it's both alive and dead. And when you open the box, the probability function disappears, it collapses, and when you make this observation, then the cat will either go into this state of being either alive or dead, but not both. Poor cat is depressed because nobody came to his birthday stroke funeral. That's a joke.